Hello students, in the previous video we have discussed about group homomorphisms and some of the examples. In this video we are going to study about kernel of a homomorphism. So what is the kernel of a homomorphism? Let us define. Let phi from G to G dash be a group homomorphism. Then kernel of phi is defined as car phi is equal to those x belongs to G such that phi of x equal to E dash. So what is E dash? E dash is the identity in G dash. So therefore, phi of x is the subset of the domain of the homomorphism which contains all those elements from the domain whose image is the identity in the codomain. So that set is called the kernel of the homomorphism. Now let us discuss some example. Number one. So we have already discussed some examples of homomorphism. So let us take the same one. So f from r star to r star defined by f of x is equal to x square. So we have already seen that this is a homomorphism. So then let us find the kernel of the homomorphism f. So then it contains, by definition, it contains all those elements from r star such that f of x is equal to what? The identity in r star. Now what is the identity in r star? This is equal to 1. Now what is this one? This one is the identity in the codomain r star. So that therefore this implies x belongs to r star such that what is f of x? F of x is x squared is equal to 1. So this implies that it contains all those non-zero real number whose square is minus 1. So clearly this is nothing but 1, minus 1 and 1. So therefore the kernel of f is minus 1 and 1. Okay. Now let us see the another example. Let f from GL to R star be a function defined by f of a equal to determinant of a. So we have already seen this is a homomorphism. Now let us find the kernel of the homomorphism f. So car of f, it contains all those a from GL to a to r such that f of a should be the identity in r star. Now what is the identity in r star? This is equal to 1. So this is equal to f of a equal to 1. So therefore those a belongs to GL to R such that f of a means determinant of a equal to 1. And this is nothing but the special linear group SL to R. So therefore the kernel of this homomorphism is SL to R. Okay, this is the special linear group of order 2 over the real number. Okay, so now let us consider another example. So which we have already seen, f from z to zn defined by f of m is equal to m modulo n. So we have again already seen that this is a homomorphism. Let us find the kernel of the homomorphism. So kernel of f, it contains those m from z such that f of m should be the identity in zn. Now what is the identity in zn? The identity in zn is 0. So this is equal to 0. So therefore m belongs to z such that f of m means m modulo n. This is equal to 0. So this implies m belongs to z such that now m modulo n equal to 0 means it implies that the remainder when m is divided by n is 0. That means n divides m. So n divides m. So that means those integer m such that m is a multiple of n. So and this is nothing but the set generated by m. So therefore kernel of this homomorphism is the set generated by m. So these are some examples how to find the kernel of a homomorphism. Okay. Now let us discuss a theorem. If f from G to G dash is a homomorphism show that kernel of phi f is a normal subgroup of G. So let us prove it. Let E and E dash be the identities of G and G dash respectively. Okay, so then there is a property of homomorphism that the homomorphism carries the identity element to the identity element. So there is a property. In the next video we are going to discuss the properties of homomorphism. So in this video we will show how a homomorphism carries the identity element to the identity element. That means the image of the identity element is the identity element in the codomain. Therefore f of e is equal to e dash. So kernel of phi is non-empty because the identity E belongs to the kernel of phi, so kernel of phi is non-empty. So first of all we show that kernel of phi is a subgroup. So before going to prove that f is a normal subgroup, we have to first show that f is a subgroup. Now how to show subgroup? We use the one-step subgroup test. So let x comma y belongs to kernel of phi. Then by the property of kernel of phi, f of x should be equal to identity e dash, and this is equal to f of y. Okay, so this is the from the definition of kernel of phi. So now we have to show that x y inverse belongs to kernel of phi. So we will take f of x y inverse. So then the property of homomorphism, this will be f of x into f of y inverse. So this is equal to f of x is equal to f of y whole inverse. This is another property of homomorphism. This says that if f is a homomorphism, then f of for any element g in the group, if f is a homomorphism from g to g dash, then for any g, f of g to the power n is equal to f of g whole to the power n, and this is true for all n belongs to integer and g is from g. So this is a property of homomorphism. Okay, so using that property we'll prove this property in the next video. So now using this property you can write f of x equal to f of x whole inverse. So this is nothing but identity e dash into e dash inverse. So this is e dash into e dash, so this is equal to e dash. So this implies that f of x y inverse is equal to e dash. So this implies from the definition of kernel, x y inverse belongs to kernel of f. So therefore kernel of f is a subgroup of G. Now we will show that kernel of f is a normal subgroup. So for that, let x belongs to kernel of f and y belongs to G. Then f of x y inverse. You have to find y inverse. So by the property of homomorphism, this is nothing but f of x into, sorry, this will be f of y. Sorry, I have made a mistake here. So this is equal to f of y into f of x into f of y inverse. This is by the property of homomorphism. So this is same as f of y. F of x means since x belongs to a kernel, so therefore f of x will be f of x e dash, and f of y inverse can be written as f of y whole inverse. So now when you multiply f of y to e dash, the result will be f of y, because when you multiply any element to the identity, the result is the same that element. So f of y into here is f of y whole inverse. So this is nothing but, so f of e dash, this is nothing but e dash. So this implies y inverse belongs to kernel of phi. Therefore kernel of phi is a normal subgroup of G. Okay, so now we will solve some problems. Okay, so let us see the first question. Question 1. Show that any infinite any infinite cyclic group is isomorphic to a group of integer z. So let us solve it. So let G be a cyclic group generated by A, and define a mapping. We have defined a mapping, say f from G to Z, such that f of G. Now the elements of G is a power of A, integral power of A. So I have considered the elements of G as A power some integer I. So we have defined the function as f of a to the power I is equal to f of I. Okay, then we have to first show that the function defined such a way is well defined. For this we see that since G generated by A is of infinite order, so a to the power I will always belongs to G for all I belongs to Z. So for any integer I, a to the power I will always belongs to G. Okay, and for I not equal to J, for two different integer I and J, a to the power I will never equal to a to the power J. Okay, a to the power I not equal to J implies A is not equal to J implies a to the power I is not equal to a to the power J. So a to the power I equal to a to the power J means I equal to J. This implies f of I equal to f of J, f of I equal to f of J. So this implies that whenever a to the power I equal to a to the power J implies f of I equal to f of J. So f is well defined. The function we have defined above is well defined. Okay, now we will show that the function f is an isomorphism. So for which we have to show that f is 1 1. So how to show f is 1 1? So let f of I equal to f of J for two different element I and J. So for any two integer I and J, we have considered f of I is equal to f of J. So this implies a to the power I equal to a to the power J. And since we have already write here that for any two non-zero element f of I, a to the power I cannot be equal to a to the power J. So therefore when a to the power I equal to a to the power J, we must have I equal to J, So therefore f is 1 1 1 1. Now we'll check f. Now we will check f is onto, and this is obvious. F is onto is obvious. Why? Because if you consider any element, any integer I, then there exists a to the power I belongs to G such that f of a to the power I will be I. So therefore for any integer I, there exists an element a to the power I belongs to G such that f of a to the power is equal to I. So therefore f is onto. Okay. Finally we will say that f is homomorphism. Okay, f is homomorphism. So let us consider two elements from G, say a to the power I and a to the power J belongs to G. Then f of a to the power I into a to the power J means this is equal to a to the power I plus J, and this is equal to I plus J, and this is equal to f of a plus f of a to the power I plus f of a to the power f of a to the power I into f of a to the power J. So therefore f is a homomorphism. So hence there exists a isomorphism from G to Z. So G and Z are isomorphic. So thus any infinite cyclic group is isomorphic to Z. Show that U10 is isomorphic to Z4. Okay, let us solve it. U10 is isomorphic to Z4. So now what is U10? U10 is the unitary group. So it contains all the natural number which are less than n and relatively prime to n. So that means it contains the numbers 1, 3, 7 and 9. So that means U10 is a group of order 4. Okay. Now we see that 3 to the power 3 to the power 1 means 3. Now this is a group under multiplication modulo 10. You all know this u10 is a group under multiplication modulo 10. Now what is 3 square? 3 square means 9. What is 3 cube? 3 cube is 7. How? 3 cube means 3 into 3 into 3 27. Now since 27 is greater than 10, so we will divide 27 by 10. The remainder will be the answer. So remainder is 7. So 3 cube is 7. Like 3 to the power 4 is 1. So thus we have seen that all the elements of U10 can be expressed as a power of 3. So therefore U10 is a cyclic group generated by 3. Cyclic group generated by 3. So thus U10 is a finite cyclic group of order 4. So from the previous example we know that any finite cyclic group of order n is isomorphic to Zn. So here U10 is a cyclic group of order 4. So therefore U10 is isomorphic to Z4. Similarly, another example you can show U5 is also isomorphic to Z4. In similar way you can show that U5 is a cyclic group of order 4, so therefore U5 is isomorphic to Z4. Okay, so now we will see the next question. Question 5. Show that U10 is not isomorphic to U12. U10 is not isomorphic to U12. So how can you show it? For this, let us find what is U12. So U10 we know U10 has 3 elements 1, 3, 7 and 9. Now consider what is U12. So U12 are the elements which consider 1, 2 is not there, 3 is not there, 4 is not there because 4 and 12 is not relatively prime. So 5 and 12 is relatively prime. So 5 belongs to U12, 6 is not belongs to U12, 7 is belongs to U12 and 9 is not, 8 is not, 10 is not and 11 is there. So U12 is also a group of order 4 under multiplication modulo 12. The operation is multiplication modulo 12. Okay. Now we have to show that U12 and U10 are not isomorphic. So if possible, let phi be a homomorphism from isomorphism from U10 to U12. It is an isomorphism. Okay. So what we have considered? We have considered if possible phi from U10 to U12 is isomorphism. Then what is phi of 3 into 3? So now 3 is an element of U10. So phi of 3 into 3 means by the property of homomorphism, phi of 3 into phi of 3. So that is equal to phi of 3 whole square. Okay. Then actually phi of 3 means 3 into 3 means phi of 9. So phi of 9 is this. And what is phi of 1? Phi of 1 is again phi of 1 into 1. So this is nothing but phi of 1 into phi of 1 by the property of homomorphism. So this is again phi of 1 whole square. Now you see, we observe that x square is equal to 1 for all x belongs to U12. You see, if you take 1 square, the result is 1. If you take 5 square means 25. Now 25 is greater than 12, so we have to divide 25 by 12. The remainder is again 1. So if you take 7 square means 49. So if you divide 49 by 12, the remainder is 1. 11 square, it is 121. If you divide it by 12, the remainder is 1. So that means for all elements in U12, the square of that element is equal to the 1. So now since phi of 3, now phi is a function from U12 to U12, so phi of 3 belongs to U12. Similarly, phi of 1 is also belongs to U12. So phi of 3 square will be 1 and phi of 1 square will be 1. So thus we get phi of 9 will be equal to phi of 1, but 9 is not equal to 1. Okay, so this implies that phi is not 1 because this is the property of 1. So what the property of 1 says, if x is not equal to y, then f of x should not be equal to f of y. Now here phi of 9 equal to phi of 1, but 9 is not equal to 1. This implies that phi is not 1. This implies phi is not 1. But this is a contradiction. Why? Because we have considered phi is a isomorphism, and isomorphism is a homomorphism which is 1 on and on 2. So that means I must be 1 on. But here we obtain I is not 1 on. So that means we get a contradiction. We get a contradiction. You get a contradiction. So therefore u of 10 is not isomorphic to u of 12. Understood? Now let us discuss another question. Show that there is no isomorphism. There is no isomorphism from Q, the group of rationals under addition to Q star, group of non-zero rationals under multiplication. Okay, so we have to show that between Q and Q star there is no isomorphism. Okay, what is Q? Q is the group of rational number under addition, and Q star is the group of all non-zero real number under addition. So let us solve it. So if possible, let there is a isomorphism. If possible, let phi from Q to Q star be an isomorphism. Okay. Then phi must be isomorphism, means phi is homomorphism on and onto. So phi must be onto. So for -1 belongs to Q. -1 belongs to Q star. So in this now -1 is in Q star. Since phi is onto, there exists some x in Q such that phi of x into, there exists some x in Q such that phi of x should be -1, isn't it? Now phi is in Q star. -1 is in Q star and phi is onto. So there must be an x in the set Q such that phi of x should be Q. Phi of x should be -1, isn't it? By the onto-ness property of phi. Okay. So now how can I write it? This implies phi of x can be written as x by 2 plus x by 2. This is equal to x equal to -1. Since phi is a homomorphism from Q plus Q star, so this is nothing but phi of x by 2 into phi of x by 2 by the property of homomorphism. Yes. So this is nothing but phi of x by 2 whole square. So this implies that now what is phi of x by 2? Phi of x by 2 lies in Q star, non-zero real number. So what this line implies that there exists a non-zero rational number whose square is -1. But it is never possible because we know that there exists no non-zero rational number whose square is -1. So that means we get a contradiction. So therefore Q and Q star are not isomorphic. So there exists no isomorphism between Q and Q star. Okay, this is the end of this video. We'll stop here. In the next video we will discuss about properties of group homomorphism. Thank you everyone.